So for the next part of this chapter, we're going to look at kinetic and potential energy. So in the previous bit, we looked at work done, and we looked at how that was the force times the distance moved. Now, some of this that we're going to be looking at is quite closely related to that. In fact, the gravitational potential energy is in effect exactly the same calculation as we looked at in the last chapter. So in the last chapter, when we looked at work done moving vertically, we said the force was in effect the weight, mass times by gravity, and the distance moved was the height. Now this is the same for the energy stored as gravitational potential energy, which I'm going to call GPE. That is equal to mgh. So the mass times gravity times the height. Now don't forget, in terms of the height, that is related to our zero energy or zero height position, which we define in the question ourselves, depending on what's happening. Now, the other type of energy, which we mentioned briefly but didn't look at, was the kinetic energy. Now, the kinetic energy is the energy that's stored in an item as a result of the fact it's moving. And this is found using the equation half mv squared. Now, what this is telling us is that the energy in a moving object is a product of both its mass, so a heavier item has more energy, and its velocity, again, so a faster moving item has more energy. Now, the last part of this section is also looking at the fact that work done, which we looked at in the last section, is also very closely related to energy. In fact, the work done is the change in energy. So we're going to look quite specifically at this time at the fact that it's the change in kinetic energy, which we can look at as half mv squared, so the final velocity, the kinetic energy from the final velocity in any situation, take away the initial kinetic energy. Okay, now also the fact that we talked about the fact gravitational potential energy and work done, we said that when we lifted an item, we did work, so we were doing work, there was work done vertically, and that related to the fact that there's been a change in energy, so a gain in gravitational potential energy. Alright, so I'm going to go straight on to looking at 3 examples of how this works. So the first one of these I've got here. So particle of mass 2 kilograms is moving at a speed of 5 meters per second. Calculate its kinetic energy. And we're just going to jump straight into using the equation that we just talked about. So we've said kinetic energy is equal to half mv squared. So in this case, that would equal half times 2 times 5 squared, which would equal 25 joules. Okay, which we generally just write as a J. We talked about joules last lesson being the unit that we used for energy. And that's it. Simple as that. Now do be careful that it is velocity that we're talking about, so it does have direction, but in here we're not looking at the direction, as we're only looking at an instant in time, so we're taking that 5 meters per second. Alright, now the second example I'm going to look at is this one, which is looking at gravitational potential energy this time. So a 7 kilogram bag is lifted from the floor to a height of 1.2 meters. calculate the gain in gravitational potential energy. Now what I'm going to do here is my object, which is 7 kg, and I'm going to lift it up to here. It's still 7 kg. Now the reason why a diagram's a little more important here is we need to define this as our zero potential energy, or our zero height. And so we've got a height here of 1.2 meters. Then all we're going to do to work out our gravitational potential energy is use mgh, which is equal to 7 times 9.8 times 1.2, which equals, and I've forgotten my calculator, so I'm going to put it as 8.4 G. And again, that would be measured in joules. The final example I'm going to look at is more of an applying situation. So it's bringing a couple of the areas together that we've done. So we've got a cyclist with a mass of 110 kilograms accelerating along an 80-meter stretch. We've got an initial speed and we have a net force. So we're not talking about resistances and force from the cyclist, it's just an overall net force in this question. So as with any good mechanics question, the way to start is with a diagram. So we've got our 80-meter stretch here. And we have our cyclist who is 110, has a weight of 110 G's at either end, and we have an initial velocity of 2 meters per second and a final velocity that we do not yet know. Okay, so there's a couple of steps to this. First of all, we need to look for our work done. Now, we know that we're applying a force of 45 newtons. And from the work we did in the last section, what we can say from here is that work done is equal to force times distance, which is equal to 45 times 80, which gives us 3,600, and it's joules again here. Now, relating to what I talked about earlier in this section is the fact that work done is also equal to the change in kinetic energy. So in this case, that's going to give us 3,600 is equal to half mv squared minus half mu squared. Now, just to save a bit of writing, I'm going to factorise that out a little bit. So we get half times 110 v squared minus 2 squared. So now it's just a case of rearranging that and solving to get our unknown v. So we're going to go 3,600 divided by 55, which is our half and our 110, is equal to v squared minus 4, which gives me v squared is equal to 69.45 by doing my divide and then adding my 4 on. So finally, to work out my velocity, I just square root that, which gives me 8.33 meters per second. And that's the 3 significant figures. And that's it done. That's the velocity, the final velocity calculated. Let's straighten that up a bit. That's the final velocity calculated given those initial conditions. And that is how work, kinetic energy, gravitational potential energy and work done all linked together. So what I suggest you do now before the lesson is have a go at questions 1, 2 and 3, which are on page 71 of the textbook. And if you want any further help with anything, there are more examples and a few more notes going from page 68 to page 70 of the textbook.